Hi everyone. So in this video, we're going to be starting a new topic called transformations. So transformations are a really important and big topic in this class. So we'll probably be spending about 5, maybe even 6 videos on transformations. So I just want to start by kind of giving you an idea, a rough idea of what transformations are before we get into anything specific. So transformations basically are talking about changes to a graph or a formula of a function. So transformations refer to changes in the graph of a function. And when I say changes, what do I mean by that? I mean changes like shifts. So when I say shifts, I mean taking a graph and kind of pushing it up or down or left or right. It could also refer to a reflection. So reflections in a graph mean flipping it. So flipping it horizontally, flipping it vertically, those are examples of reflections. And then the last type of transformation we'll be talking about is a stretch, so stretches. So that would be like taking your graph and making it taller or pushing it down to make it kind of shorter or stretching it horizontally to make it wider. Those would be stretches. And so how are these changes in the graph related to changes in the formula? Well, basically, depending on what kind of changes you're making to a formula for a function, that will tell you what the corresponding change in the graph will be. So these changes basically are the result from altering the formula of a function. And when I say altering, I mean that we're doing things like adding. So like adding a number to your function, or subtracting a number from your function. Negation, so we'll get more into what I mean by that in a later video, but negation basically just means making something negative, so taking your function and making it negative. And then the last one would be multiplication, so multiplying a function by a number we'll see affects its graph a certain way. I actually meant to write multiplication, not multiplying. So yeah, basically the idea is that we're going to graph things not by kind of plotting points, but more by looking at what are the changes that have been made in the formula of this function and using those ideas to sketch the graph. And this is something that's really important because it will continue to come up, especially in Pre-Calculus 2. It's going to be really important that you know how transformations work, as well as in later calculus classes. So when we're doing our transformations, we'll usually be kind of starting with one of 4 basic functions. So here I have graphed 4 different functions, and we'll talk about what the formulas are for these. But these are basically functions that you should be familiar with what their graph looks like. So we will usually be applying transformations to these basic graphs. And so sometimes these are called parent functions. And I think the idea is that if you have kind of an original graph and then you do some changes to it, it's like you have the parent function, and then I guess the new function is like the child function. I don't know. I don't really like to call them that, but I'll just write it here because you might see it come up somewhere else. So yeah, so what are the kind of most important ones that we'll be using? So this first graph, and this might be a good place to pause and see if you can remember yourself, just like by quickly looking at them, which functions each of these are. So this first one is f of x is equal to x squared. This next one is f of x is equal to absolute value of x. And then again, here you might want to pause and just see if you can remember what the formulas are for these two shapes. So this one is f of x is equal to square root of x. And this last one is f of x is equal to x cubed. So basically, the idea behind transformations is that if you are familiar with just a few basic graph shapes, it really opens up the door for being able to graph all sorts of different types of functions. Because what we're going to be able to do is sketch graphs that look like these four, but with some kind of a change. You know, maybe the graph has been moved a certain direction, maybe it's been stretched, maybe it's been flipped. And so that's why it's so important that you're familiar with these four graphs, because that's kind of our starting point, right? You need to know the starting point in order to be able to graph like the change, right? So let's jump into actually trying to understand what transformations are and how they work. So what we're going to do is I know I said that we're not going to be like, transformations are about, you know, graphing without making tables. However, when we're first trying to figure out how transformations work, I do want to make tables because I think it will help you see why the transformations work the way they do. So the way that this video is going to go is that rather than me just tell you, oh, hey, here's the rules for transformations, we're first going to work through a couple of examples so that you can see for yourself why the rules work the way they do. And in order for you to really see it yourself, that's why we're making the tables. But once we've established what these rules are, then you won't have to make tables anymore. Then you can just apply the transformations directly. And if you don't quite get what I mean by that, don't worry. I think it will become clear when we get into our examples later. Okay, so the quote unquote parent function we're working with here is going to be f of x is equal to x squared. So we're going to be applying transformations to this. Okay, so let's start by just filling out a table for f of x is equal to x squared so that we have some points that we can graph. So if we plug in -2 squared is 4, -1 squared is 1, 0 squared is 0, 1 squared is 1, 2 squared is 4. And so I'm just going to plot those points. And we can put a couple more points on this. So -3, if we square that, that gives us 9. +3 gives us 9, just to get a little bit more of an idea of what the shape is. So it gives us this parabola shape. Okay, so that's f of x is equal to x squared. So now what we're going to do is we're going to make a new function called g of x. And the way that we're going to create this function g of x is by taking f of x and changing it in some way. So specifically what we're going to do is we're going to, in this case, take f of x and we're going to add 1 to it. And we're going to see what effect that has on the graph so that we can see how does the transformation in the formula affect the transformation in the graph. So the first thing I want to do before we go and fill out our table, let's actually just write this as kind of like a more normal looking formula. So this goes back to, I think like the first week of class, I had you do some examples where you had to do things like f of x plus 1. So what does it mean to take f of x and add 1 to it? Well, it means you literally take your function. So what is f of x? F of x is x squared, right? So we have x squared, and then we just add 1 to it. So f of x plus 1 is x squared plus 1. And so now when we go and fill out the table, that's the formula that we can use to evaluate our outputs. Okay, so if we plug in -2, we have -2 squared, which is 4, and then we add 1 to that and we get 5. Then we have -1 squared, which is 1, and we add 1 to that and we get 2. Then we have 0 squared, which is 0, we add 1 to that, we get 1. 1 squared is 1, we add 1 to that, we get 2. 2 squared is 4, we add 1 to that, we get 5. So I'm going to go ahead and plot those points. And we'll see how this looks. I'm just also going to plot, if you plug in -3 and +3, you would get 10, right? Because you'd have 9 plus 1, which is 10. Okay, so how would you describe how the new graph compares to the original graph? Like just what visually, what has happened to the graph? So it's moved up by 1, right? So the transformation that we see is that the graph has shifted up 1 unit. And so how could we make sense of like why did that happen? You know, what is it about this transformation that caused the graph to shift up 1 unit? Why didn't it go like right by 1 or down by 1? You know, why was it that it specifically went up by 1? So the key lies in looking at these tables, right? So notice that on these tables, the x coordinates are all the same on these points, right? I put the same values on the table, so the x coordinates are the same. What happened to the y coordinates though? Well, if you compare these y coordinates with these ones, the y coordinates on the new function each are 1 higher, right? We added 1 to each of them. So because the way this function worked is that we took our original function and we then added 1 to it, that had the effect of increasing all of the y values on the graph. And I think maybe the best way to think about it is that, remember f of x, when you're talking about the outputs of a function, or sorry, when you're talking about f of x, you're talking about the outputs of a function, right? And those are the y values. Those are y coordinates. So if you're taking your function and adding 1 to it, that means that you're taking y values and adding 1 to them. And so that has the effect of moving everything up by 1. So I'll write down specifically, we added 1 to each y coordinate. So what would this have looked like if we had instead done x squared minus 1? So if we had subtracted 1 from each y coordinate. Well, then it would look like the original function, but shifted down by 1, right? So then all of instead of the table looking like these y values, instead it would be like 3, 0, -1, 0, 3. We would be subtracting 1 from each of these values. So basically, whatever you're either adding or subtracting to your original function is going to directly impact the graph by shifting it either up or down by however many units you're adding or subtracting. So I want to kind of fill out this general table. And so this general table, or this table that we're going to fill out, is going to be true for any function. So the whole idea behind transformations is that they work for any function. So if you have some kind of an original function, some basic function that you are familiar with, if you do a certain change to that function, regardless of what the function is, the change is always going to kind of show up the same way in the graph. Okay, so what was the change that we made in this case? Well, we basically took our function and we added some number, right? We added 1 specifically, but here we want to be more general. So let's just say we're taking a function and we're just adding any number c. So what is that? How is that going to show up in the graph? Well, it's going to shift the graph up c units, right? If we had added 2, the graph would have gone up by 2. And let's get to that third column in a second. I just also want to write down this other one, which was that if you do f of x minus c, so now let's say you're subtracting, and here by the way, we're assuming that c itself is positive, right? So that adding c means you're adding a positive, subtracting c means you're subtracting. So what would that do to the graph? Well, that would actually then shift it down c units. So what do I mean by this third column? Well, for now, this might seem like it's not super important, but I think when we get into more complicated transformations, I just want to make sure everyone is very clear on how, like literally what to do to your graph to get the effect that we're describing. So what do you do to your graph to shift it up by c units? Well, you add c to every y coordinate, right? That's what we did in our example. And sorry, my screen is stuck. There we go. Every y coordinate. And similarly, would you shift your graph down by c units? Well, then you would want to subtract c from every y coordinate. Okay. So we're going to do another example with a vertical shift in a moment, but I first want to see, I want to kind of do another example kind of like this, where discover another transformation together. And then once we have, another rule established, then we'll go and do some like more examples. Okay, so this example, we're also going to be working with the original function being f of x is equal to x squared. So we can just fill out this table the same way. And we'll sketch the graph again. I guess I could have just copied and pasted the one before, but that's okay. And, okay. So that is our original graph. And so this time we're going to make a new function, and let's call it h of x. And so this one is, instead of taking 1 and adding it to f of x, we're going to take 1 and add it to x. So basically what we're doing is, instead of adding 1 to the output, we're adding 1 to the input. So how would we write this as like a kind of a nicer formula, one that we can actually understand? Well, again, this goes back to that, that video towards the beginning where I had you practice a bunch of like evaluating functions at expressions. So if our original function is x squared, how would we write down f of x plus 1? Well, it would be x plus 1 squared. Right? I know there's a lot going on because of the h of x. Maybe ignore the h of x for a second, pretend that's not there. And if I had asked you, if I told you f of x is equal to x squared, and then I asked you to evaluate f of x plus 1, you would just say x plus 1 squared, right? And so what's the deal with h of x? I'm just trying to give a new name to this function, right? So that we can actually just like call it by something other than f of x plus 1, because f of x plus 1 is kind of an awkward name for a function, right? We should give it kind of a new name that is just like a normal function name. Okay, so you might notice that I made this table have slightly different x values, and we'll see why that is. It's basically so that it's easier for you to see how this transformation works. So you could, if you wanted to, by the way, multiply this out and get x squared plus 2x plus 1. But for our purposes, I'm going to leave it as it is because, again, I think it'll just make it easier for us to see why things are working the way they do. Okay, so let's start by plugging in -3. So what do we get if we plug in -3? Well, we would get -3 plus 1, which would give us -2 inside the parentheses, right? And then we take that -2 and square it, and we get 4. So then next we want to plug in -2. So if we plug in -2, we would have -2 plus 1. So -2 plus 1 is -1. Take -1 and square it, we get 1. So next up we'd plug in -1. So -1 plus 1 is 0. Take 0 and square it, and we get 0. Now we plug in x is equal to 0. So we'd have 0 plus 1, which is 1. 1 squared is 1. And finally, we plug in x is equal to 1, and we have 1 plus 1, which is 2. 2 squared is 4. So let's go ahead and sketch this graph, and then we'll talk about like what's really going on here. So we have -3, 4, -2, 1, 0, or -1, 0, 0, 1, and 1, 4. And then I'm just going to plot the one additional point that is at a height of 9 just to finish out this shape. Okay, so before we get to like why this happened, how would you describe what happened in this graph? So it shifted, but this time it shifted to the left, right? It didn't shift up or down, it shifted side to side. So this graph, it shifted left by 1 unit. So why did that happen? So there's kind of two things I want to get at here. So first of all, why do you think that instead of this being a vertical shift, so instead of this moving either up and down, why do you think it moves side to side? Like, what is fundamentally different? Why in this case did our function go up or down, specifically up, but why was it a vertical shift in that case, whereas in this case, it moved side to side? So it really has to do with the fact that we're changing the input rather than the output, right? So like, just think about how inputs for your function, those are your x coordinates. And so when you apply a transformation where you're doing something to x, so you're adding or subtracting from x, that's always going to be a horizontal shift because you're not altering the outputs, you're altering the inputs, and the inputs are the x coordinates. Whereas in this example, we were adding 1 to the function, right? We left x alone. It was just f of x. F of x was normal. Where did we add the 1? We added it to the entire function. And when you're talking about the entire function, well, then you're talking about the outputs, which are the y coordinates. So that explains why our shift was horizontal rather than vertical. So now the question is, why did it go to the left? And this is, I think, the thing that probably is the most confusing part for a lot of students. You might look at this and you would think, well, +1, shouldn't it be going to the right? You know, usually when you add a number, that would go this way. Just like when we added a number outside, it went up. So this really comes down to basically the values on the table and kind of looking at how things worked, like what x values we had to plug in to get certain y values. So for example, if we look at the original function, when you plug -2 into the original function, you get 4. So how do you get 4 in the new function? Well, not by plugging in -2, but by plugging in -3. So notice that the y coordinate of these 2 points, and let me highlight them on the graphs as well. So this is the point -2, 4, so that's this point here. And then here we have -3, 4. Those 2 points have the same y coordinate, but their x coordinates are different. And so why is it that this is a shift to the left? Well, notice that basically because you're adding 1, so because you're adding 1 to x, that allows you to plug in a smaller x value and get the same output, right? Because here what you're doing is you're taking whatever your input is and you're squaring it. And maybe let me actually highlight a different number that might even make this a little easier to look at. Let's, instead of highlighting one where the x coordinate is negative, let's do one where it's positive, because I think that will make it even easier. So let's look at the point 2, 4. So that's here. And then on our other function, we have the point 1, 4. Let's focus on those points. Okay, so for the original function, you would take 2 and square it and get 4. For the new function, because you're adding 1 to it, if you want to get an output of 4, you no longer have to plug in 2, you only have to plug in 1, right? Because when you plug in 1, well, you're adding 1 to it, so you're making it bigger, and so you can achieve the same output with a smaller input. Again, I think this is one of the hardest things to understand, so it's okay if you don't get it right away, and this is one of those things that I also think that you might need to kind of sit down and think through it yourself. I think there's some things in math where as many times as someone else tells it to you, it's not necessarily going to stick. You have to really kind of convince yourself. So what I would do is really focus in on this table. Think about, why is it that you're getting the same outputs with different inputs? And I think if you really focus on that, then you can understand why it is that by plugging in smaller inputs, you get the same outputs. And that causes the graph to shift left, right? So these inputs are all 1 less than these inputs, whereas the outputs stay the same. And so that gives us this horizontal shift to the left by 1. So let me just describe what that actually looked like in the graph. So if you're shifting to the left by 1 unit, that means that you're going to subtract 1 from every x coordinate. Okay, so let's summarize that on our table here. So now if you have a function where instead of adding or subtracting to the function, now you're adding or subtracting to x, that's always going to be a horizontal shift. And so if the number, if you're adding, what that's always going to do, and let me just fix this. What that's always going to do is it's going to shift your graph left by c units. Whereas if you're subtracting, then it's going to shift your graph right by C units. So again, the reason that it works backwards is basically this idea of what kind of X values do you have to plug in order to reach the same Y values. And that's what kind of causes it to go backwards. It's because by adding or subtracting from your input, you kind of have to compensate with the X values you're plugging in order to get that same output. So what would this actually look like in the graph? Well, we said that for shifting left by C units, that means that you're going to subtract C from every X coordinate. Whereas if you're shifting to the right, then you're going to add C to every X coordinate. So basically, I mean, what I would say is, I really encourage you to try to get to the bottom of it and understand why it is that the horizontal shifts work backwards. But at the end of the day, if you want to just kind of memorize a fact, the fact that you have to memorize is that they work backwards. So vertical shifts go the way that you would expect. Addition goes up, subtraction goes down. Horizontal shifts are backwards. So when you add, it actually makes your graph go left. When you subtract, it actually makes your graph go right. Okay, so like I said, these examples were really here for us to kind of understand why transformations work the way they do. These next examples we're going to do, we're actually going to kind of apply the transformation rules without making any tables. Okay, so the first example we're going to do is we're going to use transformations to graph f of x, or actually let me call it g of x, is equal to the absolute value of x minus 3. Okay, so whenever you're using transformations to graph something, the first thing you need to figure out is what is the kind of basic familiar graph that this is a transformation of. And so in this case, because we see the absolute value, what's the function we want to compare this to? We want to compare this to f of x is equal to absolute value of x. So our original kind of basic graph that we're comparing this to is f of x is equal to absolute value of x. And so now we need to figure out, like, what is this transformation? How does our new function g of x compare to f of x? How could we express it in terms of transformations? So if our function is g of x is equal to absolute value of x minus 3, let's think about how we could write that. I want to write it basically like one of these. I want to either write it as f of x plus something, f of x minus something, or adding or subtracting inside the function. So we need to figure out which one of these four this actually looks like. So notice that the subtraction, it's not to x, right? It's to absolute value of x. And so that's what tells us that this is actually f of x minus 3. So by the way, just to kind of give comparison, if instead our function had been absolute value of x minus 3 like this, well then that would be f of x minus 3, right? Because basically if you're making a change to the input, that's going to show up inside the function. Whereas if you're making a change to the function as a whole, that will end up outside of the function. So you're always basically trying to see, are you adding or subtracting from x or from kind of the whole function? And so that's not what we're dealing with here. Here we're dealing with f of x minus 3. So the next question is, what kind of a transformation is that? What is that actually going to do to our graph? So we know that if you add or subtract from your function as a whole, that's going to have the result of shifting your graph vertically. And we also know that for vertical shifts, that they go the direction that you would expect. So if we're subtracting 3, that's going to have the effect of shifting our graph down by 3. So let's start by sketching the original graph first. So f of x is equal to absolute value of x looks like this. And by the way, it's like, I mean, I wouldn't say that you are always going to draw the original graph first, because that might seem like that's, you know, slower. Like why would you graph two graphs? But right now I'm just kind of doing it as a reference, but I think the more practice you get, you know, you'll be able to actually sketch these graphs without sketching the original one. That's why it's just so important to be familiar with what these original basic graphs looks like. Okay, so we're going to take this entire graph and shift it down by 3. And what that means is that we're going to subtract 3 from each of the y coordinates. And so really what I would just do is take this point kind of right at the V and move that down by 3. So that goes to the point -3, 0. And then from there, you can just kind of mimic the shape, right? We know that the absolute value graph, it just kind of goes up like a V, and it has a slope of 1 on the right and a slope of -1 on the left. And so we can just kind of fill it out like that. So that is our transformed graph. Okay, so let's do another one. So in this case, we're going to again use transformations to sketch h of x is equal to the square root of x minus 2. So the first question is, you know, what is the basic graph that this one is a transformation of? So we see that there's a square root, and so the graph that we want to compare this to is f of x is equal to square root of x. And so now the question becomes, you know, what is the transformation? Like, how would we write this as a transformation of the square root of x? So we have h of x is equal to the square root of x minus 2. So we want to think, how would we write that in terms of f of x? You know, would this be basically, would it be like f of x minus 2, or would it be f of x minus 2? And so notice that in this case, to kind of contrast it with the last one, in this case, the subtraction was happening outside of the absolute value. And so that corresponded to subtracting from the function as a whole. Whereas in this example, we're not doing, it's not this, right? It's not h of x is equal to square root of x minus 2, right? The minus 2 is inside of the square root. And so that's what tells us that we want to rewrite this as f of x minus 2 in parentheses. So by the way, if it had been what I drew in red, well, then it would be, sorry, I didn't realize I'm actually probably going off the screen a little bit. So if it was like this, if it was square root of x minus 2, well, then it would be f of x minus 2, because that would be happening on the outside of the function. But again, that's not what we have. We have it on the inside of the function. And so what is this going to look like in the graph? Well, we know that if you're making an addition or subtraction to the input, it's going to be a horizontal shift because you're changing the x values. And we also know that for horizontal shifts, they go the opposite direction of what you would expect. And so instead of shifting to the left by 2, we're going to shift to the right by 2. So let's sketch our original graph, and then we'll do the transformation. So the original graph looks like this. So remember, it's like half of a sideways parabola. And I would just, if you just know a few points on it, so like it goes through 0, 0, 1, 1, 4, 2, and 9, 3. Just by kind of knowing square roots of numbers, then you can sketch the graph. So what is this one going to look like? Well, it's going to look just like this one, but we're going to just move every point to the right by 2. So maybe let me highlight a few points here that we can kind of track where they're going. So if we highlight these points, if we just move each of those points to the right by 2, sorry, I just moved it by 1 instead, by 2. And then this one would be here. Oops, sorry, here. You don't want to change the y value, just the x value. Then you will get the graph. And by the way, I think, like I said, I do want you to get to the point where you can do this without making a table. And it might at this point seem like, why wouldn't you just make a table? Like that just seems so much faster and easier. And it's for a variety of reasons. One is that, and we'll see this in the next video, there are some examples where if you're given a graph that doesn't have a formula, so if you're just given just like a function that is just some weird graph without a formula, then you can't really do it with a table. You really have to know your transformations. And then the other thing is, like I said, just trust me that when you get to further on classes, you're going to find it really useful to be able to think of how graphs look in terms of transformations. That being said, if you're still kind of stuck on this idea of like, why is it going right? You know, why isn't it going left when you're subtracting? If you actually plug in some numbers, I think you'll see why. So for example, on the original graph, we have the point 4, 2, right? Because the square root of 4 is equal to 2. So the original graph just takes your input and just takes the square root of it. And so that's why we have the point 4, 2 on our graph. And so what is the corresponding point on the new graph? Well, on the new graph, we have the point 6, 2. So why is it the point 6, 2? Well, because if you plug in 6, so if you do h of 6, that would be the square root of 6 minus 2, which is the square root of 4, which is 2. So basically, because you're subtracting 2, that allows you to plug in a bigger number and still get the same output, because you're subtracting 2 from it before you take the square root. And so that has the effect of moving everything to the right, because you're plugging in bigger numbers and still getting the same result. Okay, so we're going to do one more example. This one's going to be kind of going the other way. In this case, what I want to do is I want to find an equation for this graph. Okay, so we're going to use transformations basically to figure out what the equation of this graph should be. And so the first step is to figure out, what kind of a shape does this have? Out of our kind of basic library of functions, which one is this one? Or which one is this one a transformation of? So this one looks like the graph of f of x is equal to x cubed, right? It looks like a cubic graph. So now we're kind of working backwards. So instead of looking at the formula and figuring out what the transformation is from that, we have to look at the graph and figure out what the transformation is. And then from there, we can write the formula. So in this case, what is our transformation? So how would we describe how this graph compares to the original function f of x? Well, it's been shifted to the right by 5 units. Nothing else has changed, right? So it hasn't gone up or down, it's just shifted to the right by 5 units. And so what does that tell us? So let's say maybe we're going to call our function g of x. That tells us that our function g of x should be f of x minus 5, right? Because how do we get a shift by 5 units to the right? Well, in order to do a horizontal shift, we have to be working inside the parentheses. We have to be changing x, not f of x. And then in order to get it to go right and not left, we need to subtract. And so we do f of x minus 5. And so how would we write that as, like an actual nice formula? Well, our original function is x cubed, right? And so what would f of x minus 5 look like? It would look like x minus 5 cubed. And so that is our formula. All right, so that is it for this video. So in the next video, we'll basically just be practicing with shifts. So we'll see that you can apply multiple shifts. So you can have a function where you're shifting it, left or right, as well as up and down. And then, as I said, we'll also be looking at an example where we're going to be working with a function that doesn't have a formula. So kind of just like a weird random function and applying transformations to that.